Okay, good evening, everyone. Um, Welcome to the 12th lecture in ECE 560. Before we get started, do you have questions or comments? Okay, so quick announcements before we get started. One is about the upcoming project presentations that's due in about 2 weeks. So I put up a poll on Canvas. It's in the form of a quiz, and that's going to help me understand what would be the format of your presentation. So there's three options. You could either go for a live presentation over Zoom, or you could do a pre-recorded version. I'll create a link for people who want to upload it, or you could do a presentation in class. So it's up to you. You decide the mode of presentation. But once you indicate your preferences, I will provide you a schedule if you're going to present live. So, and by the way, the pre-recorded presentations will be also uploaded on Canvas so that everyone can take a look. The last option is about in class. Okay, so up till now, I think we've covered most of the contents in this course. There's going to be a few more topics which are kind of supplementary, but the good thing is that no more technical stuff is going to be tested. We just have one more homework and one more quiz. So the homework this week will be a MATLAB based homework. So there's no more computations involved. You will just use MATLAB and do the exercise. And the purpose is twofold. One is to help you understand how to implement LQR, LQG controllers in MATLAB. And the other is to help you also use those things in your projects if you want. So there are a lot of people who haven't implemented anything in MATLAB. So I think this tutorial-like homework is going to help you implement some things and also use that in your projects, if you will. The last quiz is going to be the week after this, and that's going to be a review quiz. So no more new information is being tested. It's a quiz on the fundamentals of the course. So basically, everything from the start to the previous lecture, all the fundamentals on stability, on very basic things of this course. So I think it should be very easy for everybody and also help you, some of you, to improve your grade if you want. So remember, there's one homework being dropped and one quiz being dropped at the end. But on top of that, I think this last homework and last quiz is a very basic ones. So hopefully people can catch up on their grades. The other thing I wanted to say is about course feedbacks. So I think you must have received notifications about it. So it's important to make sure that you submit your feedbacks in time, because the college and the department takes it very seriously. So make sure that you're able to fill in the course feedbacks within the time. Last thing in the announcements is, since this is Ramadan right now, and many of you might be observing. So we will try to end our lecture around 8 o'clock, at which point, some of you might have to leave. So feel free, if we go overstretch, feel free to leave, and I will also try to make sure that we finish around 8 o'clock. Okay, so let's start with today's topic. We are not going to touch new information. I'm just going to continue the discussion that we started last time and also give some alternative methods. So first method is about an alternate way to solve the algebraic Riccati equation. So previously we have seen a method to solve the AREs, and that was based on assuming a matrix with with some coefficients m1, m2, m3, and so on. And then eventually we had a set of linear equations that we would solve, and that would give us the solution to the Riccati equation. But there is a more efficient way, and mostly for computers, to solve these equations, and that's called an eigenvector method. So computational tools like MATLAB are comfortable doing eigenvectors, eigenvalues, and other matrix operations. So this method will be more friendly for computers to quickly reach the solutions to algebraic Riccati equations, even for larger ones. So the Riccati equation generally is of the form, specifically the algebraic one is of the form 0 equals P times A plus A transpose times P minus PB R inverse B transpose B plus Q. So the first thing we could do is we could start to represent this as a matrix equation. Right, so let's represent this as as this expression. So let's write P here minus identity. This is an n cross n identity. And then let's have a matrix H in the middle and a vertical matrix with again an identity and a P. So identity is again an n cross n, and at the end let's put equals 0. Right, so we just want to transform the Riccati equation into this this formulation, and this H here can be written as A minus B R inverse B transpose. Here we will have minus Q minus A transpose. I am not able to hear you. Is somebody's trying to say something? Let's see if the volume is. Okay. Anyway, if somebody's trying to say something, then you can post in the chat. Okay, so this H is this matrix, and if you try to expand this formulation, you will see that it eventually goes back to the Riccati equation form. So the H is actually called a Hamiltonian matrix, right? So H is called a Hamiltonian matrix of size 2n cross 2n. Okay, and we can obviously see that this is a n cross 2n matrix, and this one here is a 2n cross n matrix. So if you try to multiply them, then eventually your result is going to be an n cross n, right? And basically, if you solve this for p, that is the solution of the Riccati equation. So let's see what is the benefit of using this formulation. So we'll have to do a few steps here. Let's pre-multiply by x inverse and post-multiply by x. So I'm just going to write here what it looks like after the x has been added. So it's this times h times ib times x equals to 0. Right, so if you do it on both sides, basically nothing happens on the right side, but here you will have x inverse times this formulation times x. And now what we are going to do is we will take this inside, so it's x inverse p, then we'll have minus x inverse times h times ix times px equals 0. And then we're going to convert this into an eigenvector and eigenvalue formulation, right? So this this second thing here this can be equals to by the way, this I will not be here because identity, right? So ix is simply x. So this is going to be x px times capital lambda so if h times x px equals x px times lambda, then this lambda is the matrix with eigenvalues of h. So this is a matrix with the eigenvalues of h on its diagonal. Right, so what happens is if you, by definition of the eigenvalues, basically if ax equals to lambda x, right? So if you multiply a matrix A with a vector x, and the result turns out to be some constant time that vector, then this is the eigenvalue and the x is the eigenvector. So I mean, in this case here, we're trying to multiply h with a vector. And I mean, it's obviously not a vector, it could be a matrix here. So the idea is similar. So H times this thing here is this thing times a constant. So this lambda will be a diagonal matrix of eigenvalues of the matrix H. Okay, so if we were to diagonalize, if we were to convert this into eigenvector and eigenvalues, we could represent this thing here as xpx times this capital lambda. Right. So in other words, this capital lambda will be a matrix S1, S2, and Sn, and zeros everywhere else. Okay, so for simplicity, we just assume here that that at least the eigenvalues have at least n distinct distinct ones. So we assume that H has at least n distinct eigenvalues among its 2n neighbors. Right, so which in other words means that H times Vi, so H is the matrix, Vi is the eigenvector, equals SIVI, right? So where Vi is the ith eigenvector and Si is the ith eigenvalue. Okay, so if we write this together, basically the matrix H times V1, V2 to Vn can be, basically this thing here is x times px. Right, so this can be written as this V1, V2, Vn times the diagonal matrix S1, S2, all the way to Sn. Right, so this was lambda, and this thing here is that again x px. Right, so now if this vector v1, v2, all the way to vn can be split up as follows, is as wz with the w invertible, then by comparison, so if you compare this, then x equals to w and px equals to z. Okay, so in other words, this will result in p equals to ZX inverse, right? Or it's the same as, because X is W, so it's going to be ZW inverse, right? So that's the solution of Riccati equation. So therefore, the solution of ARE is actually E equals ZW inverse. And we just have to figure out what is a Z, what is a W. Right, so ZW is are two portions of this eigenvector matrix. So let's quickly write down the steps to find the solution to the ARE. So number one, we find n eigenvectors of the Hamiltonian. The Hamiltonian H. So basically you get vectors v1, v2 up to vn. Then what you do is you express the stacked vectors. So this is v1, v2, all the way to vn. Then this matrix you have to express as wz, right? The top portion is w, the lower portion is z, right? And we will see how this can be done. So we have to do w inverse. So we just pick the n by n portion as w, and the remaining is the z. Okay, so if we've done this, then the last piece is easy. Oops, I messed up. Just give me one moment. Yeah, so okay, I don't know what is happening here. So then the solution to the Riccati equation is simply P equals to ZW inverse. Okay, so that's a more computationally efficient way of solving Riccati equations. And probably if we have, we will definitely see an example on this. Okay, so let's look at some of the key implications of this result. So first thing we want to consider is how does this impact the poles of the closed loop system. So when we talk about the closed loop system, it's really x dot equals to a minus bk x, and the k is basically R inverse B transpose times P, right? So these are so the poles really are the eigenvalues, right? So the poles of the closed loop system are eigenvalues of H. So this is where the previous formulation plays a role. So if you found the Hamiltonian, basically the poles of the closed loop system are actually the eigenvalues of the Hamiltonian H. And these poles are in the complex plane C minus, meaning the left half of the complex plane. Okay, so the fact to know here is that the Hamiltonian has n eigenvalues in C minus, and n eigenvalues in C plus if and only if AB is stabilizable and AC is observable. Okay, so if it is stable, then everything is in the left half plane, but if it's stabilizable, then the n eigenvalues could be in the positive half plane, and meaning that it could be controlled and brought to the left half plane. So here's just a quick comment on the role of Hamiltonians in the system stability and pole locations. Next, we will look at an example where we can make use of what we just saw. The example is an old one that we have seen many times. So let's look at a more simplified one. So consider the following system. X dot equals 2x plus u, and a performance index j equals 0 to infinity x squared plus ru squared dt. So looking at the performance index, basically it's x squared. So q is identity, right? No, q is 1. Because generally it is x transpose qx. So if it's simply x, because it's a one-dimensional state space, so the q is simply 1. And r is the capital R is simply equals to the small r. Okay, so the problem statement hasn't finished yet. So it says the system is controlled using an LQR controller So find the value of R such that the optimal closed loop system has its has its pole at 3, at -3. Okay, so we are looking at an LQR, and it also tells you to do some pole placement, but luckily that pole placement is controlled with this parameter R. So really what we have to do is to find the LQR controller, meaning find the K, and then you know, that would be in terms of the small r, and then we use that K to find A minus BK, find the poles of the system, and eventually find the small r that will result in the pole to be at -3. So we are going to make use of the matrix method to solve the, or the eigenvalue method to solve the Riccati equation. So let's get started with the LQR controller. So for an LQR, we know that U equals to minus KX and equals to minus R inverse B transpose M hat X, and the M hat is a solution of the Riccati equation. So M hat is the solution of of 0 equals M hat A plus A transpose M hat minus M hat B R inverse B transpose M hat plus Q. Right, so first thing we will do is to use a traditional way. So in the traditional way, what we did is we made an assumption about M, right? I mean, in this case, it is simply a 1-by-1 matrix. So since the system is 1-by-1, so M hat equals to small m, right? And the equation is basically it becomes 0 equals to 2m plus 2m minus m squared over r plus 1. So what we get here is m squared minus 4 rm minus r equals to 0. So if we solve for m, we will get 4r plus minus 16r squared plus 4r divided by 2. So what you get is 4r plus minus 2 square root of 4r squared plus r over 2 equals to 2r plus minus square root of 4r squared plus r, and eventually we pick the positive root, and it becomes m is 2r plus minus plus square root of 4r squared plus r. So that's your value or the solution of the algebraic Riccati equation. And using this, we can directly find the controller. So basically K was 1 over R times M. And it simply just becomes 2R plus square root of 4R squared plus R over R. So we have 2 plus the square root of 4 plus 1 over R. Okay, so this was a K, and now the closed loop system pole or let's start with the closed loop system. Is governed by A minus BK. So A minus BK will be 2 minus the K is 2 plus and the B is 1. So we get 2 plus square root of 4 plus 1 over R. And we want to make sure that the pole, which is the value itself here, because it's a 1 by 1, so equals to minus 3. Okay, so what this means is basically 2R plus square root of 4 plus 1 over R equals to 5. Right? What is it? Versus? Yeah, so it's 2. Yeah, okay. So next we have to solve for R, right? So basically, oh, so then we didn't have to even go here. Let's just say that the 2 will cancel with the 2, right? This goes with this, and what we get is 4 plus 1 over R square root equals to 3. Right, so 4 plus 1 over R equals to 9. 1 over R equals to minus 5. No, it's plus 5. So basically R equals to 5. Oops, 1 over 5. Right, so that's the result. And again, that's using the conventional method. And let's see if we do this with the Hamiltonian, what do we get? So Hamiltonian, first thing is to express the Riccati equation in the form of a Hamiltonian. So we already saw that the Hamiltonian H can be written as H is the matrix A minus B R inverse B transpose minus Q minus A transpose. So if you plug in the values using the system, we will have 2 here, minus 1 over R, and a minus 2 here. Right, that's the Hamiltonian. Now the next thing is eigenvalues of H. And luckily, we know that the eigenvalues of H are directly the poles of the closed loop system. So if you want to find the eigenvalues of this matrix, you can get to the roots of the characteristic polynomial. Okay, which is basically determinant of Si minus H. So if we do the determinant of S minus 2, 1 over R, plus 1, S plus 2, we will get S minus 2, S plus 2, minus 1 over R equals to 0. So this results in the quadratic equation S squared minus 4 minus 1 over R equals to 0. And eventually S will be square root of 4 plus 1 over R. Right, so okay, luckily we directly found the pole of closed loop system, right? Because it is the eigenvalue of the Hamiltonian. Okay, now the question is, the pole should be at -3. So basically what we are trying to say is 4 plus 1 over R square root equals to -3, which says 4 plus 1 over R equals to 9. And eventually 1 over R equals to 5. So therefore R equals to 1 over 5. All right, so we see that using the Hamiltonian method, we didn't have to go to all that extent. We could directly find the poles of the closed loop system and modify those poles. So the important thing to understand here is that we were looking at an LQR controller, but we also want to think about the location of poles of the closed loop system. So that gives us the next thought that's the thought about whether we can design a controller which could do both pole placement and LQR. All right, so remember, we've been talking about two different controllers. We started off in this course and we said, so there's a state feedback controller, right? And the important distinguishing part of this controller is we do pole placement here. Right, basically that's the starting point of this controller. We know where we want to put the poles of the closed loop system, and we use that state feedback to place those poles in those locations. So and we said, this is the most basic controller, and what we could do next is to find a performance-based controller. Instead of looking at the pole locations, we could look at an linear quadratic controller, right, an LQR. And this is an optimal controller. With a performance index, right? Minimizing a performance index. We specify a function j, which is a linear quadratic function of the state and the inputs. And basically, we try to optimize that cost function, and the resulting controller or controller gain is called a LQR. Now, what we are thinking about is, can we find a middle ground here? Right, so we want to find optimal controller with prescribed poles. Right, so it's a mixture of these two controllers. So we have a performance criterion that we want to optimize, and also we would want to make sure that the poles of the closed loop system are placed at the locations we want them to be. Previously, this was not possible. We designed an LQR, and then we figured out where the poles are, and we had no control over them. But with this strategy, we are thinking of whether we can do this joint design. So optimal systems, optimal control. With the prescribed poles. So for a multi-input controllable system, so this is the important fact we have to leverage. So if there's a controllable system with multiple inputs, x dot equals to ax plus bu, the controller u equals to minus kx, that shifts the poles to the prescribed locations, is not unique. Right, so that is the fact we will exploit here. Remember, when we looked at the MIMO systems, we said, there's flexibility in the controller gains. There are some gains that have to be fixed, but others could be chosen arbitrarily. So we will try to make use of this property here. So we can leverage this to assign the poles S1, S2, Sn, and to minimize. First criteria is that the closed loop poles are S1, S2 up till Sn, and we want to minimize the index j equals 0 to infinity x transpose of t q x of t plus u transpose of t r u of t dt, d tau actually, right? Because the actually doesn't matter here because it's 0 to infinity, so t is just a dummy variable. So to achieve this, we can use the controller in a specific form. So we can apply u equals to minus kj x plus uj. right? So kx is like the feedback gain, and then uj is like an extra input, right? So we use this form to recursively shift one pole to a prescribed location. So one pole at each step to a prescribed location. If we were to use this input, then the closed loop system will be the following. So x dot will be a minus b kj x plus b uj, right? So this, let's call this as matrix A J. J uh, is the index, or it is the identifier of which pole is being shifted. So if this was the AJ, this differs from the original system in by only one pole. So if the matrix A has the set of poles, then AJ is going to place the jth pole to the location that we want it to be. Okay, so now for the similarity transformation, x equals to tx tilde the original system and the cost j, they become x tilde dot equals to t inverse at x tilde plus t inverse bu, which is by definition a tilde x tilde plus b tilde u. Now j tilde becomes the cost function, also gets transformed. So we will have x tilde transpose t transpose q d x tilde plus u transpose ru dt. And again, by definition, this becomes 0 to infinity x tilde transpose q tilde x tilde plus u transpose ru. Right, so the system can be transformed into something in x tilde, and the cost also gets modified with something q tilde. Okay, so next thing is using the Hamiltonian. So both Hamiltonian h and h tilde have identical eigenvalues. So what that means is h tilde, which is t inverse 0, 0 t transpose times h times t o, or 0 basically, T inverse. So if you take the determinant of Si minus H tilde, what you will get is identity 0 minus Q tilde Si minus A inverse identity 0 and identity here times Si minus H. So this can be written as Si minus A tilde B tilde inverse B transpose 0 Si plus A tilde transpose minus Q tilde Si minus A tilde inverse B tilde or inverse B tilde transpose. So then determinant Si minus H tilde equals determinant of Si minus K tilde times determinant of Si plus K tilde transpose minus Q transpose Si minus A tilde inverse times F, where F is simply this. So assuming A is diagonalizable, the A tilde equals T inverse AT, and it could be written as lambda 1, lambda 2, lambda n, where lambdas are the eigenvalues, and assume Q tilde equals to Qj tilde, and this can be written as there's a 0 here, and then there is Qjj. The rest are all zeros. So I mean, it can be shown that the determinant of Si minus H equals the determinant of Si minus H tilde. So in essence, they have the same closed loop eigenvalues. Now, so if they are the same, you can actually evaluate them to be the product I not equal to j, I equals to 1 to n, s plus lambda I, s minus lambda I, times s plus lambda j, s minus lambda j, minus qj, qjj tilde, fjj. Okay, so the thing to note here is that this is the piece which creates the shifting of poles. Okay, so therefore the pole lambda j is shifted to Sj by selecting Qjj tilde to be Sj squared minus lambda j squared over Fjj. Right, so that's the result that we have to consider. Now we can compute Qj equals T inverse Qj tilde T inverse and solve the Riccati equation, which is A transpose Pj plus Pj times A plus Qj minus Pj B R inverse B transpose Pj equals to 0. So then the solution to this will be the Pj. So then U will become minus R inverse B transpose Pjx plus Uj. Right? Or in other words, you can say it is minus Kjx plus Uj. So using this will shift only one pole closed loop system. X dot equals to A minus B Kjx plus B Uj, but which is by definition Ajx plus B Uj. Right, so that pole will be shifted to its specified location. Okay, now the idea that we saw here can actually be extended. Because right now we only placed one pole to the desired location, so we can extend and continue this idea to obtain U as minus the sum of J times Kjx. The P, which is a solution of Riccati equation, can be the sum over J of Pj. And the Q can be the sum over J of Qj. Right, so this is so we will have to iteratively solve for each J, but the process is the same. And important thing is that this is a hybrid controller. And that will place the poles at prescribed locations. And also minimize the cost function. Okay, now, so that's the end of this hybrid controller. I just want to give you the overview. It's hard to solve these type of controllers by hand. So, you know, knowing this is good, but eventually if you want to do this, I'm confident there are packages there and you can leverage them. But the important thing is to understand the idea of what we're trying to do here. So we are trying to combine the benefits of both worlds and mix it into one controller in the form u equals to minus kx, but this k is now a summation of multiple k's, and each of them is going to place the controller, place the poles of the closed loop system to a new location. Now, so just to catch up on some of the missing things that we didn't do earlier, I would like to put up a few examples. One example that we couldn't do earlier is about LQG controllers. So let's try to do that. And then there's one more example on the case of that's on the case of reduced order Kalman filters. Now, so last time we saw a very complicated derivation of a reduced order Kalman filter. So today we can look at least a simplified example so that there's some clarity. So LQG is a linear quadratic Gaussian controller, and the question says design an optimal output feedback controller for the accelerometer with constant disturbance represented by x1 dot equals to x2 and x2 dot equals to u plus a, and y equals to x1 plus w. And eventually, a dot equals to 0, right? Because it's a constant disturbance. So if you go and recall your previous lectures, basically we start off with considering A as not existing, and then try to expand the state space and solve for the larger space. In this particular example, we have already solved before. So let's quickly repeat the process. This is the state space model, and the y is 1, 0 plus w. Now remember, w is this Gaussian noise that we want to take into account. Previously, we didn't have this, so this is a Gaussian or normally distributed noise, right? And it has some characteristics in terms of the variance. So first step was to, or maybe before that, there is also the performance index. So okay, so it's performance index is okay. Important thing is now a expected value, right? So J is an expected value of t to infinity x1 squared tau plus u squared tau divided by c squared d tau. And then we close the expected value. Now from here, we can see that the Q matrix will be 1 zeros and R matrix will be 1 over C squared. Okay, let's move to the next slide here. So we've seen this before, but let's draw the architecture. This is the plant with the dynamics, and the output has that noise. Noise is only at Y. So basically, some W is being added here. There's an input U to the system, and because it's a LQG, so we have to have two things. One is the state estimator, and the other is the noise. But obviously, noise can be considered to be 0, and that will make it a reduced order Kalman filter. So there was a Kalman filter here, which takes in the output Y and also the input U and gives you a X hat, right? That's the state estimate. And then what you're going to do is use the minus K here, and that becomes the input U. Okay, and the Kalman filter structure is again like an observer. So X hat dot equals A X hat plus BU plus L hat Y minus CX hat. And this piece was the Kalman gain, right? The gain of the observer. So so as we have seen before, in LQG controller, we can exploit the separation principle, and and we first design the controller without noise. So due to the separation principle, so we can design the controller separately, right? Assuming no noise case. So if that's the scenario, then the optimal controller is U equals minus KX hat or minus R inverse P transpose M hat X. That was the also the LQR, but we can ignore the noise and start with this first, and eventually we will use the noisy case to determine the Kalman filter gain. So M hat is the solution of zero equals to MA plus M plus A transpose minus M B R inverse B transpose M plus Q. So I mean, we can recall our previous results, and we can ignore A first and solve this equation, and remember the way. So if we ignore A, then K hat will be R inverse B transpose M hat, which becomes C squared 0, 1, M1, M2, and M2, M3. It's C squared, M2, and M3. Right, and then next thing is to solve the Riccati equation. So 0 equals M1, M2, M2, M3 times A. So we have 0, 1, 0, 0 plus A transpose. And then we have M1, M2 minus minus M hat. Then we have B transpose C squared 0, 1, and then M1, M2 and finally we have Q, which is 1, 0, 0, 0. So simplifying this, we get 0 M1 plus 0, 0 M1, M2 minus M1, M2 C squared M1, M2, M2, M3 plus 1, 0, 0, 0. So further simplifying this will give you 0 M1, M1, 2, M2 minus M1, M2, M3, 0, 0, M2 C squared, M3 C squared. Plus 1 all zeros. And then we get minus M2 squared C squared, M2, M3 C squared, M3 squared C squared, plus 1, 0, 0, 0. Minus M2 squared C squared plus 1 M1 minus M2 M3 C squared, M1 minus M2 M3 C squared, and then we have 2M2 minus M3 squared C squared. All right, so if you try to solve this, basically you have three equations. M2 C squared equals to 1, which gives you M2 is 1 over C. And then we get 2M2 equals M3 squared C squared, gives you M3 squared is 2 over C squared, eventually square root 2 over C3/2. So we mainly required M2 and M3. So K, which is a controller gain, is C squared M2 M3. And it's basically C and square root of 2C, if you kind of simplify this expression. Okay, so you've got the K. Now so your U will be minus CX1 hat minus square root of 2CX2 hat. And I'm also going to put minus A here because coming from your previous example. Right, I mean, I can solve this again for the larger state space, but we already know that the disturbance A is going to be removed at this stage. So basically, so previous lectures, I think maybe it's in lecture 10. So you can get rid of the A directly and move to the next step. So next step will be to solve for the Kalman filter. So we already designed the U equals to Kx. Basically Kx Kx hat. And maybe I should go back and put a hat here as well. So, so the next step is how do you find the X hat? Right? So X hat is the output of the Kalman filter. And Kalman filter expressions you also know. So let's go and take a step-by-step perspective. So now we need to design a Kalman filter, which means X dot hat equals to AX hat plus BU plus L hat Y minus CX hat, right? And the goal is to find the L hat, right? And we know the expression, so let's first look at the system. So here's the system, the A dot. Expanded state space is following. And plus a 0, 1, 0 U. And the output Y is 1, 0, 0, X1, X2, and A plus W. So the optimal Kalman gain can be obtained by L hat equals P hat C transpose W inverse, where P hat is the solution of the Riccati equation. 0 equals to A P hat plus P hat A transpose minus P hat C transpose W inverse C P hat. So if you solve for P, and remember W is the covariance matrix. So basically, if you solve for P hat, you can get optimal gain L hat as L1 hat, L2 hat, and L3 hat. Right, I'm not going to solve it here because it's computationally intensive. So assuming you solve the Riccati equation, then the Kalman filter is as follows. So x hat dot equals A x hat plus BU plus L hat y minus CX hat. So it's going to be this is the A matrix, and then x hat plus 0, 1, 0 U plus you replace the L hat with the vector that you've obtained, and then you put y minus x1 hat. Oops, C is what? So C is 1, 0, 0, and then yeah, so we are left with only x1 hat, right? So it's a 1 by 1 matrix. Okay, so if you have this, then we get x1 hat dot equals to x2 hat plus L1 hat y minus x1 hat, and x2 dot hat equals A hat plus U plus L2 hat y minus x1 hat, and then A hat dot equals to L3 hat y minus x1 hat. Okay, so that's how the Kalman filter is going to be implemented, and this x hat you will use with the gain controller gain and complete the system loop. So therefore, the output feedback controller that minimizes the cost J is given by the controller gain K, and the Kalman gain L, where the controller is designed using LQR for the noise-free case, and the Kalman filter is used to estimate the state using noisy measurements and the input. That's the summary of the LQG. We start off with the noise-free case and first find the controller gain. That's just like an LQR procedure. And then you use the noisy case and come up with the state estimator. And that will require the noisy measurements and also the input. And just like we did in this example, you just have to find the optimal Kalman filter gain L, and then use it in the system architecture that we saw here. So this is the plant. The Kalman filter will have a replica of the plant, except that you will have X hats here. So once you find the gain L, you can construct this block. Its output is going to be an X hat, and which is fed back to the plant using a controller gain K. Okay, so now I just want to do one small example that's related to the reduced order Kalman filter. Again, we were not able to see this in the last lecture. So let's try to do an example. So consider the dynamic model of the pendulum. Which we saw earlier also, theta dot equals to omega and omega dot equals to capital omega squared theta plus u plus b. And y equals to omega. And the v here is the white noise. Okay, so now we want to, so interestingly, there's the noise in the output is 0, right? So Kalman filter cannot be constructed directly because it requires W inverse. Right? So W is a covariance of the output noise, and if W is 0, then W inverse is undefined, so you cannot find the Kalman filter directly. So we'll have to go to a reduced order filter. So reduced order Kalman filter is required, and So let's follow the steps here. First thing is to do the state space, right? That's a no-brainer. This is equals to 0, 1, omega squared 0, theta omega plus 0, 1 u plus 0, 1 b. So this is the A matrix. Here's the B matrix, and remember this is the F matrix. The output y equals to 0, 1, theta, and omega w. So this is the matrix C. So for a reduced order Kalman filter, we saw last time that C times L hat equals to identity. Right, so this result is coming from lecture 11. So so C is 0, 1 here, L hat is equals to identity. So basically, if you compute it, you can see that L hat is going to be 0 and 1. Okay, and then next thing is to do a transformation. So we do a transformation based on what we saw last time. So the transformation is constructed as follows. There's C on the top, UL I minus L hat C, where UL I minus L hat C is composed of n minus L rows of I minus L hat C. Which are linearly independent of C. So, so I minus L hat C is can be computed as identity minus L hat is 0, 1, C is something like this. So we are looking at the identity minus we will have a 0 here, a 0 here, and a 1 here. Right, so we get 1, 0, and 0, 0. So first row is independent, right? This is independent of C. So we pick this, and so T is simply 0, 1, 1, 0. Now using this T, basically A bar is TA, T inverse can be written as the following. Times A matrix. A was 0, 1, omega squared 1. 0, 1, 1, 0. And this turns out to be 0, capital omega squared 1, 0. This first element is called A11, and this one is A12, A21 is A22. So last time we we said that the dynamics of the reduced order filter are as follows. So gamma 1 dot equals to 0, gamma 2 dot equals to A22 bar, gamma 2 plus A21 bar, y plus UL I minus L hat C BU. So plugging in the values, this was 0, this was 1. This we already computed as 1, 0. B is 0, 1. So so the dynamic will look like gamma 1 dot equals to 0, which is gamma 1 of t equals to 0 for all t. And the gamma 2 dot equals to y. To compute this, then so now comparing and remembering our previous results. So recall that gamma was equals to t zeta, where zeta equals x hat minus L hat y. So we still need to transform the system to to obtain the x hat dynamics. Okay, so basically if you convert this this is gamma here. So if you proceed with the transformation, then eventually the reduced order filter will be of the form theta hat. Right, this is x hat. So x is basically theta and omega. This is x1 hat. Right, so this is going to be um, 0 L hat Y plus zeta, and zeta is basically the T inverse of gamma. So what you will have is 0, 1, and then you will have gamma 2 here. So therefore, basically, if you compute this, you will get gamma 2 dot equals to 1. So I guess the reduced order filter is a little more complicated to understand, and it's and the idea is you kind of go from the original state and come to something called a gamma. Gamma is the transformation of zeta, and zeta is the displaced state x. So from the original x, you have you went to something called zeta, and then zeta is transformed to gamma. So your reduced order filter is only on the on one of the states, and it's simply gamma 2 dot equals to y, and there's multiple transformations happening there. But essentially the idea is that you've been able to get rid of the singularity problem that occurred because of the no noise in the output y. So at this point, I think we have covered all our material that we wanted to talk about. And in view of Ramadan, basically, I wanted to make sure that we end around 8 o'clock instead of our regular lecture, so it can accommodate students who are observing. Now, again, repeating the the announcements. I think we are left with one quiz and one homework. In fact, homework will be so homework 6 uploaded or due this week. It is a tutorial style homework, so hopefully you wouldn't have to spend a lot of time doing it, and you can focus more of your time towards the project. So this tutorial style and based on MATLAB. Okay, that's one thing. The other is quiz 6 will be uploaded next week. And again, this is a very generic and I would say a summary quiz, or very fundamental quiz. So it's a fundamental and covers basic and foundational concepts of the course. So if you have, the fundamentals well understood, I don't think you will have any problem doing this quiz. And of course, if there is, the lectures are all open and you can refer to them anytime during the 1 hour of the quiz. And I think it shouldn't be that hard for you to spot the answers. There's no computation needed, just identifying true or false or things like that. Now the other important things are, just reiterating them, is the poll quiz for project presentations. Right, so due by tomorrow. By tomorrow, you have to indicate how you are going to do your project presentation, whether it's online, whether it's a recorded one, or whether it is in class. So just take this quiz by tomorrow so that I have a clear view of who is scheduled for the virtual presentation, and we can make a schedule. The other important thing is about mid-review feedbacks. So I am working on them, and hopefully by the weekend, I will get back to everybody. So some of you have contacted me personally, and unfortunately, I haven't been able to respond to everyone, but I'm coming to it soon. So by this weekend, I hope to reach out to everyone and inform you about the comments, which you can incorporate in your next couple of weeks to do the presentation. And remember, you can still update your final project reports after the presentation. We will have one more week, and the final reports are due April 28th. Okay, last thing is about course feedback. So very important, please make sure everybody fills it out by within the time frame. And that's it. So any questions? Is everybody okay with everything?
Yes.
Yes, Professor.
Yes, Professor.
Okay. All right, so I think we are almost there. We close to 8 o'clock, so let's meet next time. Next will be our last lecture in this course, and I'll hopefully try to not cover much new information and just give you more tutorial-like and a different type of content. So let's meet next week, and after that we will look forward to your presentations and the project. Okay, so have a great rest of the week. I'll see you next Thursday.
Thank you, Professor.
Thank you, Professor.
Thank you, Professor.